The objective today is to look at some of the Euclid theorems that are related to the center of a circle. So, do you know any of the theorems? Can you mention any of the theorems that deal with the center of the circle?
The turn chord.
It's a theorem, but it's not directly related to the center of a circle.
Oh.
Yeah, let me show you why I'm saying that. All right. Let's say we have a circle here, né?
Yes.
And we have a tangent there. Let's call this point T. The center of the circle is here. Let's call it point O. The chord can only be drawn from here to there. Then we have a tangent, which is this line, né?
Yes.
And then we have a chord. Let's call this point, let's say A. Hello, Sabata.
Hello, sir.
All right, welcome to the class. We just started. We only started with the theorems which deal with the center of a circle. If you see my screen, you'll see that I've drawn a circle here. There is a center there, né?
Yes.
And then I have a tangent there. But the problem is the tangent we see here has nothing to do with the center of this circle, né? And when we talk of the turn chord theorem, the turn chord theorem talks about the angle that is between the tangent and a chord, which is this angle. So, then the angle which is formed down here must be equal to the angle at the alternate segment, okay? And you clearly see that this has never, it never made use of the center of the circle. Therefore, when we talk of the theorems that deal with the center of the circle, we cannot include the turn chord theorem. Are we together?
Yes.
Yes, sir.
Good. So let's still think of the other theorems which will make use directly of the center of the circle. Think about them and tell me, which other theorem do you think will make use of the center of the circle?
Radius perpendicular to chord.
To radius is perpendicular to tangent, not the chord, né?
Turn chord. Oh.
Let's check this. I have a circle once again. I'm going to try to form a tangent. And the tangent is formed here. Once again, I'm calling this point T. And I'm calling this the center of the circle. Now, if I write point O here as the center of my circle, then I draw a line from O to join point T. Then that is my radius. This one we can clearly see that, no, this is coming directly from the center of the circle. Ne? If it's coming from the center of the circle and it's touching the tangent, then we say the radius is perpendicular to tangent. All right? Are we together, guys?
Yes, sir.
Good.
Yeah. Yes.
Okay. So one of the theorems that we can say is related to the center of the circle is that the radius is always going to be perpendicular to tangent. Although it's not a main theorem, but it is one of the axioms that we pick from grade 10, grade 11 stuff. Né? Now, what other theorem can we say is related to the center of the circle.
Yes. Angle at the center twice angle at the circumference.
Michelle, do you agree?
Yes.
All right, so we have the center of a circle here. And we talk of the angle at the center. Let's say this is the angle at the center. Obviously, the center has been mentioned. This angle at the center, and we have an angle at the circumference. If this is called x, or let me use some values. If this one is 100 degrees, then the theorem says that this angle must be what?
50 degrees.
It has to be 50 degrees. That is why we say angle at center is twice angle at circumference. Ne?
Okay.
So it deals with the center of a circle, and it says that the angle at the center is always going to be twice the angle at the circumference. So we have two, right? One is a radius is perpendicular to tangent. The other one is the angle at the center is twice angle at the circumference. Try to think of other ones and tell me which other theorems do you think deal with the center of the circle?
Angles, I think it's angles in the semicircle.
Angles in the semicircle. Well, let's try that and see. Michelle, do you know the angles in the semicircle?
Yes, sir.
Okay.
One of the angle must be 90 degrees.
All right. That is the angles in the semicircle. So let's say this is still our center. I've cleaned that tan chord because that one we agreed that is not related to the center. Ne? So
Yes,
let's
sir.
say I draw this as a diameter. This is still my center. And because the diameter has already passed through the center, then this theorem deals with the center of a circle. So if an angle is subtended right at the circumference of that circle, then we can say that, let's look at this. This is still angular center. Do you agree?
Yes, sir.
Angular center. Because that diameter you see there, if this is point A, this is B, this is C, the diameter you see there subtends an angle here already. It subtends this angle, which, because this is a straight line, then this angle must be what?
180 degrees.
180 degrees. If that line subtends an angle at the circumference, then it only has to be half of this 180. Do you see that? So this then has to be 90 degrees right there. So there should be 90 degrees right here. So, but for standard reasons, instead of saying angular center is twice angular circumference, we will only say, oh, this is angles in a semicircle, which is the acceptable reason. All right, which other theorem can you think of, guys? Now we've been able to mention three. Radius is perpendicular to tangent.
I think radius perpendicular bisect or is perpendicular to the chord.
No, radius is not perpendicular to the chord. Reframe. I see the theorem you are trying to talk about, but reframe it. Give us the correct theorem.
You first said the radius bisects a chord.
I see you are getting there, but you are not there yet, both of you. Because remember, I showed you this, that the radius is perpendicular to tangent. There is a certain theorem where a radius, it's not actually a radius, but there is a line from somewhere and it bisects a chord. Get that theorem for me. What does the theorem say?
Line from center bisect the chord.
Line from center bisects the chord, but the line must be a certain line before it can bisect the chord. Mm-hmm. All right, let me help you guys. This is what the theorem says. You see this new red circle, right?
Yes.
Okay. There is a theorem which says that if we draw a circle and we have a chord, and there is a line from the center of a circle, a line like from this center of the circle, and it goes straight to join the chord. Guys, let's try to understand something, that this line ON, is it a radius?
No.
It's not, right?
No, sir.
So the theorem does not involve a radius. It is just an ordinary line. An ordinary line which has touched, what is this line AB? How do you call this line AB?
A chord.
That is a chord. So it's just a line from the center which has touched a chord. We cannot just say that, oh, because it has touched the chord, it's going to bisect the chord. No. It can only bisect the chord if this line ON touch the chord such that they form perpendicular. Are you with me, guys?
Yes, sir.
Yes.
That is the only way we can now say that, oh, because the line is from center and it is perpendicular to the chord, then the obvious thing is the line must now be bisecting the chord. And so these two sides, these two lengths should be equal. But if it's just any line which is moving from the center and it touches a chord and doesn't show that it's perpendicular, we have no reason to say that, oh, it's going to be perpendicular to the chord. I mean, it's going to bisect the chord. Are you with me?
Yes.
Yes.
Very good. So a line from center which is perpendicular to a chord bisects the chord. Good. We've mentioned 1, 2, 3, 4. Think of another theorem and tell me. I'm listening, guys.
I say.
Yes. Is that all you can remember?
Yes.
Okay. Let me quickly put another diagram here. Maybe it will draw your attention to it. And there is also a center. I have a chord here. And somebody tells you that there is a line from the center. The line, nobody has mentioned it. Eh? Nobody has mentioned that it's perpendicular.
Yes.
But all we can say is that if this is A, this is B, and this is C with P here, the only thing the person is saying is that, oh, this line has met, I'm talking of line CP, has met line AB, but when they met, they are equal here. This side and that side are equal. What does this mean to you? Let's look at the first one. Here there is a line coming from the center. The line meets this chord AB, but it meets it at 90 degrees. And because of that, we can say, oh, then AN is equal to NB. But now look at this. There's a line from center, yes, which is CP. The line met this chord AB. But when it met the chord, it only bisected the chord. What does it mean? What does this mean to you? What conclusion can you make from this diagram?
So I think we should say like something like AP is equals to PB.
Yeah, that is already shown here. Those are the things we say is given. Eh? It's given that AP
Yes.
is equal to PB. It's given that there is a line from center. The line has met chord AB. How it met it, nobody knows because the diagram doesn't say. So based on what you see here, what can you conclude? What can you conclude? Let's check this one once again. Ne? Once again, here, you were given that there's a line from the center. You were given that there's a line from center, which is ON. And you were given that ON is perpendicular to AB. And because of that, you said, ne? Are you following?
Yes, sir.
Yes, sir.
Because of that, you said that then AN must be equal to N. Must be equal to NB. This was given in the diagram, ne? And you said this.
Yes.
This must be equal. In this case, what is given?
The two equal lines.
Yes, you were given that AP is equal to PB. So what should be your conclusion?
Since the lines are equal, it means that CP bisects equal angles, meaning that it's the converse theory.
It's the converse. Yes, it's the converse of
theorem.
Yes,
Theorem.
This is the converse of this one, right? It simply means, let me guide you guys here. It simply means that then CP is perpendicular to AB. Just as in this one, we managed to say that if this is perpendicular, then these are equal. Here, if these are equal, then this is perpendicular to AB. I believe it's clear, ne?
Yes, sir.
Yes.
Very good. So these are the theorems that for now we can say that they relate to the center of a circle. They relate to the center of a circle. We can even talk of another theorem, which is if a line is already perpendicular to the circle, perpendicular to a chord, then the line will pass through the center of a circle. That one is also there. But for now, let's concentrate on these five, ne? And draw our attention to that.
Yes, sir.
This one, the theorem is what? Radius is?
Perpendicular to
tangent.
Perpendicular to tangent, right? And this one, what does it say?
Angle in a semicircle.
Angles in a semicircle. This one is what?
Angular center twice angular the circumference.
Very good. Angular center twice angular circumference. This one?
Line from center perpendicular to chord.
Will do what?
Bisect
the chord. This one, what does it say? This is line from center, which is perpendicular to a chord, bisects the chord. This one, how do you frame this one?
Yes.
It's not difficult. Just go. You said it's converse most. So just reverse your statement, and you see the theorem will come. Okay. Then let me show you. This one we said is a line from center which is perpendicular to a chord. Look there. Line from center perpendicular to a chord. This is the line from center. It's perpendicular to this chord. And so it must bisect the chord. That's why these are equal. But if we come to this,
Yes.
this is a line from center which has already bisected the chord. A line from center which goes to the midpoint of a chord. Because it has bisected the chord, then the line has joined the midpoint of the chord. This is the midpoint, P. Therefore, a line from center to the midpoint of a chord is perpendicular to that chord. Did you get it?
Yes.
Good. Line from center to the midpoint of a chord is perpendicular to the chord. But this one is line from center, which is perpendicular to a chord, bisects the chord. All right. Now let's try to mix some of these theorems and see how we'll be able to apply them in a typical exams question. Let's say we have this circle, and then we have a center. We have a line from the center, and the line joins this chord. What can you say about this angle? If these are equal, what can you say about this angle?
It's a 90-degree angle.
90 degrees. See, now we are using the converse of that theorem, right? So let's say this is our center. So the first thing which should come into our mind is, this one must be 90. And if this is 90, what about this one?
90.
And this?
90 also.
90 also, right? Very good.
Yes.
But look at what I'm going to do. I'm going to form this with this. Okay. And then form this. Let's assume that this is a straight line, the diameter, right?
Yes.
Okay. Now, if it's a diameter, let's look at this angle. Let's give it names here. Let's call this 1 and 2. And we said this must be 90 degrees. Guys, if angle O1 is equal to 40 degrees, you guys must tell me the size of angle C and Y.
Angle C is 27.
And why?
Because it's angle at the center twice angle at the circumference.
It's angle at the center twice angle at circumference. Michelle?
Yes.
What will be the size of angle C?
It's 20 degrees.
20 degrees. It doesn't mean you are agreeing with Sabata.
Yes.
Good. So C would then be 20 degrees. C will be 20 degrees, and the reason is angle at center is 2 times the angle at the circumference. Ne? All right. But look at the diagram carefully, guys. We said this is 40. If this is 40, ne? And this becomes 20.
Yes.
But do you see this line? Look at OC. OC, ne? What name do we call this OC?
It's a radius.
So where else do we see a radius in this circle?
OB.
OA.
OB, OA, right?
Yes.
Yes.
There is another angle which is 20 degrees. Find it and tell me. If O1 is 20, O1 is 40 like we said, then there is another angle which must be 20 degrees. Which angle is that?
I think it's DC.
B? Why do you think it's B? You mean this angle?
Yes.
Why do you think so?
Because
I think it's angle A.
Angle A? Do you mean this one?
Yes.
Why do you think so? Sabata, you can still give me your reason, eh? Who wants to give their reason first? Sabata, you said it's B. Michelle says it's A. Michelle, your reason?
OA is equals to OC and
OA is OC and
base angles of a triangle are equal.
base angles of the triangle, base angles of the triangle. You know something, ne?
Yes.
Sabata, I'll come back to you, ne?
okay.
That base angles of a triangle, you might be right, but for standard reasons, the acceptable reasons which you need to put down in the examination, we don't accept base angles of a isosceles triangle. What we accept is that they are angles that are opposite the equal sides of a triangle. Okay?
Okay.
So we are going to say angle A. Angle A is 20 degrees because they are angles that are opposite the equal sides of a triangle. This is the acceptable reason, not base angles. The angle at A, this angle will be equal to the angle at C because the two of them are angles that are opposite. You can clearly see they are opposite each other. Eh? But they are angles that are actually opposite these equal sides. This is a radius OA, and this is also a radius OC. So they are actually angles opposite the equal sides of this triangle AOC. So let's try to avoid other reasons. Ne? Let's go for the correct reason, which is angles opposite equal sides.
Of a triangle.
Good. You see, we have managed to say that O1 is 40. Ne?
Yes.
And then we've been able to realize that this angle here will be 90. What do you think will be the size of angle B? And why?
50 degrees.
Why 50?
The sum of the angles in a triangle
Angle B must be
is
50.
up to 180.
Yes, because it is the angle sum of
triangle.
any triangle. All right. So guys, you see the diagram, if you look at it from the start, it looks like complex. Ne? Imagine if we've not discussed this. A diagram like this in exams, we'll be like, hey, what is this? But if you try to talk about the theorems one after the other, then you realize that no, I can talk of angular center here. There I can talk of line from center, which is perpendicular to the chord. Ne?
Yes.
So when you see the questions in the exam, please try to pick the pieces one after the other. Don't pick the entire package. Don't pick the entire question. Look at this line. Oh, this is a line from the center. It is going to join a chord. When it joined the chord, what happened? It is perpendicular to the chord. Therefore, it's supposed to bisect the chord. Or when it joined the chord, it became a right angle. A right angle was formed. Therefore, it's supposed to bisect the chord. So pick it in pieces. Pick one more, and then we will end the lesson. Let's say that we have a circle here, and we have a tangent. Again, oh, my tangent, ne? We have a tangent here. And this is my center. Then there is a line which goes through that center to the end of the circle. A straight line. This is my center, guys. What is the name of this straight line?
A diameter.
That is a diameter. Now, this diameter, immediately it touches this tangent. What is supposed to happen here?
We're going to have 90-degree angles.
We are going to have a 90 degrees right there. Ne?
Yes.
So look at this. Look at this. I think it's better, a little better. Not exactly what I wanted, but let's agree that this is lying on the circumference, okay?
Yes, sir.
But okay. Yeah. Do you see that? Do you see that we have 90 here?
Yes.
And this 90, the reason is what? Why is this 90?
Radius perpendicular to tangent.
The reason is that, let me call that C1, C2, C3. C1 is equal to 90 degrees because the radius is perpendicular to tangent. Okay? Where else do you see 90 degrees?
Angle A.
Angle A, ne? Angle A is 90 degrees. Why is it 90?
Some angle triangle.
Check it again.
Angle in semicircle.
That is the angles in semicircle, ne?
Yes.
Yeah.
Angles in the semicircle. Now, do you see that we have actually said this is 90 and this is also 90?
Yes.
If these two are 90, 90, then we are now having a reason to link these two. without saying angles in a semicircle or radius perpendicular to tangent. We can now say this is 90 and this is equal to this directly because of tan chord. You see a new theorem comes in.
Yes.
Yes, sir.
So we can confidently say that C1, angle C1 is equal to angle A, which is now true
And
because of tan chord. That is why in the tan chord theorem, we say that, oh, the angle between tangent and chord equals the angle in the alternate segment. Although this is not about the angle at the centers. Ne? It's not about the centers of the circle, but it's another theorem which becomes true by looking at these two that we've just formed. We will talk about that tan chord theorem in detail, I think maybe tomorrow or another time. Ne? But this clearly goes to confirms that the tan chord theorem is also true for any angle that is formed between the tangent and the chord. All right. Let's look at this small angle. Angle C2. If angle C2, if C2, this is an if question, eh? If angle C2 is 30 degrees, which other angle can we find and why?
We can find B and C3.
We can find angle B, we can find C3. Sabata, find angle B, Michelle, find C3, and then you will tell me your answers with reasons. Ne?
Yes.
Are you done?
not yet, sir.
Michelle, do you have your answer?
Yes.
You are finding angle C3, right?
Yes.
If C2 is 30. What is your answer?
C3, angle C3 is equals to 60 degrees.
How did you get that 60 degrees?
Because of the radius bisects the tangent, it means that
Because the
both sides,
is
it's perpendicular to the tangent.
very good.
We know that both sides are 90 degrees,
90
meaning the sum of
mm-hmm.
C2 and C3 is equals to 90 degrees.
Okay.
So we're going to say 90 minus 30 degrees, which is 60 degrees.
Perfect. Ne? Thank you.
Yes, sir.
It means C3 is 60 degrees. Sabata, do you have your answer ready?
Yes, sir.
Okay. What did you get for B?
I got 60, sir.
How did you get your 60?
I said I said 180, sir, minus 90 minus 30.
Minus,
And I got
are you talking of this 90?
yes, sir.
And then this 30, ne?
Yes, sir.
And then you got 60. Michelle, do you agree with him?
Yes, sir.
Good. It means if C3 is actually going to be 30 degrees, then obviously we are supposed to have 60 degrees here from calculations and 60 degrees here. But our calculation for the 60 here, we use the angle sum on a straight line. Eh? Our calculation to
Yes.
get this 60, we use the angle sum in a triangle. You can clearly see we are getting the same angles. Once again, it goes to confirm the fact that if you have an angle between tangent ne, and
Yes.
a chord, then that angle will be equal to the angle in the alternate segment.
Alternate segment. Okay.
It cannot be equal to this angle. It cannot be equal to that angle. It has to be equal to the angle that is subtended by the same chord, which is called AC. That is what the tan chord theorem is all about. All right. Guys, I want us to bring the lesson to an end for today. Tomorrow we will pick it from where we stopped. But for the meantime, if you have anything to add, any questions you want to put across, let's do that right now. Is there any question, any particular question about what we've done today?
No, sir.
Sabata?
I think I'm okay, sir.
You're both okay, right? Perfect.
Yes.
But if it happens that you have any other questions, feel free to send your questions. You can send it via the Google Classroom, and then I'll answer all your questions. Ne?
Okay, sir.
All right. Then in that case, we will end our session for today. Thank you guys for joining the class, and hope to see you same time tomorrow.
Thank you, sir.
All right. Are you done?
Not yet, sir.
Michelle, do you have your answer?
Yes.
You are finding angle C3, right?
Yes.
If C2 is 30, what is your answer?
C3, angle C3 is equals to 60 degrees.
How did you get that 60 degrees?
Because of the radius bisects the tangent, it means that
Because
both sides,
is
it's perpendicular to the tangent.
very good.
You know that both sides are 90 degrees,
90
meaning the sum of
mm-hmm.
the sum of C2 and C3 is equals to 90 degrees.
Okay.
So we're going to say 90 minus 30 degrees, which is 60 degrees.
Perfect. Ne? Thank you.
Yes,
It means C3 is 60 degrees. Sabata, do you have your answer ready?
yes, sir.
Okay. What did you get for B?
I got 60, sir.
How did you get your 60?
I said I said 180, sir, minus 90 minus 30.
Minus,
And I got
are you talking of this 90?
yes, sir.
And then this 30, ne?
Yes, sir.
And then you got 60. Michelle, do you agree with him?
Yes, sir.
Good. It means if C3 is actually going to be 30 degrees, then obviously we are supposed to have 60 degrees here from calculations and 60 degrees here. But our calculation for the 60 here, we use the angle sum on a straight line. Ne? Our calculation to get this 60, we use the angle sum in a triangle. You can clearly see we are getting the same angles. Once again, it goes to confirm the fact that if you have an angle between tangent ne, and a chord, then that angle will be equal to the angle in the alternate segment.
Alternate segment. Okay.
It cannot be equal to this angle. It cannot be equal to that angle. It has to be equal to the angle that is subtended by the same chord, which is called AC. That is what the tan chord theorem is all about. All right. Guys, I want us to bring the lesson to an end for today. Tomorrow we will pick it from where we stopped. But for the meantime, if you have anything to add, any questions you want to put across, let's do that right now. Is there any question, any particular question about what we've done today?
No, sir.
Sabata?
I think I'm okay, sir.
You're both okay, right? Perfect.
Yes.
But if it happens that you have any other questions, feel free to send your questions. You can send it via the Google Classroom, and then I'll answer all your questions. Ne?
Okay, sir.
All right. Then in that case, we will end our session for today. Thank you guys for joining the class, and hope to see you same time tomorrow.
Thank you, sir.
All right.